In this episode, we mainly simulate white water and mist. Well, without further ado, let's get started. Delete them first. Keep these two for viewing noise later. The source of the white water is this flip with a large number of particles. To get the white water with rich details, there should be far more particles to simulate it than in the flip. Considering the computer RAM, it's better to simulate it part by part. Show all objects. Roughly, it can be divided into 3 parts. Let's add a box for part 1. Add a copy node to create 3 copies on negative z-axis. We get the length of the boxes on z-axis and the transform value here linked. As it's on negative z-axis, a minus is needed here. Then add a value here so that these boxes are overlapped on edge. This way the transition can be integrated. Besides, the boxes should box up these collision buildings. We can adjust their height as per the camera view. Check pack and instance. Now we get 3 packed geometries. Then extract them with 3 blast nodes. We import the 3 boxes into Object Merge separately. Then we can simulate the 3 parts of flip separately. Let's focus on part 1. Drop down a white water source node. Here we need to obtain a surface field and a velocity field from the particles. Drop down a VDB from particles. By default, we can get a surface field, and we can get a val based on the velocity of the points. Let's display it. Well, the res by default is a little too high. Lower it down a bit. The radius scale is too large. Lower down it a bit too. Perfect. We've got the 2 fields. There is a voxel size under volumes of white water source, albeit a bit too. It's unwise to set a high res in the beginning because the simulation time is too long and you're actually unsure whether it is good. Yeah, the res shouldn't be too low in case the simulation result is incorrect. Uncheck emit from curvature. It all depends on your needs. Only keep emission and acceleration. Regarding the white water source, the particles in flip with high velocity are enough. As to the dropping particles, we don't let them emit white water. Similarly, we can adjust the velocity range to figure out the needed range. We can roughly set the speed range between 30 to 100. Increase acceleration range too. In fact, there is no standard for these values. If you need more source points, you can decrease the mean value of the range depending on your needs. The scale of the particles is a little too large. There are 2 ways to decrease it. One way is to reduce the point radius scale. Based on the current voxel size, the point radius scale is too small to display particles. In this case, we can reduce minimum radius. Okay. Another way is to use the VDB reshape SDF node. Select Erode. Erode the surface only. The slight difference between them is that one looks smoother and the other looks more detailed. However, the simulation result is the same. Simply select it as per your needs. Currently, the white water source is solid inside. Actually, we can optimize out some invisible particles inside it. So here we set a smaller depth. Okay, keep the settings for now. For a convenient adjustment later, we can add a file cache before the white water source so that the process above needn't be calculated again, which is a handy tip to speed up your project. Get a start frame and that of flip cache linked. Set the path and the name of the cache. Drop down a null node as the surface and the velocity fields we are going to use. Besides, we can optimize the source further. For example, we can clip the source near the tsunami. This operation doesn't affect the overall effect as the clipped part is mostly blocked. We can do that as per the position of tsunami. We import the surface field here we got before. Offset it a bit on negative x-axis. Then clip it through a VDB clip node. Select Mask VDB here. Uncheck Keep Inside. OK, done. Regarding the offset value, simply set it as per your needs, as long as the simulation is not affected. After all, that operation is for a better simulation efficiency. Drop down a null node. Perfect, done with the source. Next, we create a dot network. Set start frame as -30. Let's add a whitewater object, a whitewater solver, and other necessary nodes. Import the collision object, which is the same as in flip simulation. We just copy and paste them here. Note the affector relationship emerge. We selected left inputs affect right inputs here, so keep the whitewater on the right. This way the simulation can work well. To avoid the particles slipping and bouncing, we set bounce of the ocean collision to 0. So does the bounce in whitewater object. Increase friction a bit. In fact, as long as we set 0 for bounce in the whitewater object, no matter whether other bounces are set to 0, bounce won't work. To optimize whitewater, we can directly copy subsolver 1 and paste it here. We also delete particles with low velocity or inside the tsunami. Set a lower value here to keep more whitewater on the ocean surface. Then we copy attribute wrinkle 2 and blast 4 to optimize out the particles beyond camera view. Change a group name different from the previous group. Do not make optimization steps affect the simulation. Let's continue. Drop down a pop wrinkle. Delete the particles with a depth smaller than negative 0.6. Keep the other particles as they are. Here we set it to negative 0.6. If we set it to 0, too many particles close to the surface will be deleted, which will definitely affect the lighting effect. But negative 0.6 is not a standard, so just figure out your best option through tests. Let's set up Whitewater Solver 1. Import the source first. Then import surface and envelopes. Set a slightly higher simrest than flip simulation for a more detailed whitewater. Shorten the lifespan here. There's also no standard for it. Next, we connect the size and the center in the whitewater with those in box 9. Perfect. No need to modify Forces tab. Uncheck these checkboxes under Foam tab. Keep adhesion only. Enable density control can even the particle distribution, which is unnecessary here. We also don't need enable erosion, neither enable repellence. It's used in simulating calm rivers. Our splashing simulation is fierce, so it makes no obvious difference whether to check it or not, so we uncheck it. Alright, the settings are basically done. Drop a .io. Uncheck Import Simulation Settings. Checking it merely adds some output attributes, which we don't need. Here we only need to export the particles of the whitewater. We solve one frame to check the simulation. It looks good. Next, we delete some unused attributes. Like primitive attributes and detail attributes. Delete these groups too. In point attributes, we delete UV and other unnecessary attributes. Drop down an attribute cast. Let's check these attributes. We can compress age, depth, and velocity. Keep the position as it is in case it goes wrong. Let's cache it. It's done. Here we use color preview to color it. This node was made before. First, import depth in bind, then input values in source min and source max. Fit the range 0 to 1, then connect it to ramp parameter node. We can set colors for some common attributes through it. Let's display the particles based on depth. The green particles are the spray. They fly too high and far away, and the dynamics looks too fierce. So we can add air resistance to limit them. Let's check those with a depth greater than 0. Here they are. Set a larger value here to scale down the range of spray affected by air resistance. drop a pop jack, you can test the proper value of air resistance in simulation. Besides, I like to limit them further based on velocity, because the dynamics will lack variance if all the particles are applied with same air resistance. Similarly, we need to figure out the proper min and max values. Here, my option is the min of 5 and a max of 50. So here we set the velocity range to 5 to 50 and multiply air resistance with velocity. If the velocity of the particles is less than or equal to 5, apply an air resistance of 0.015 to them. As to those with a velocity equal to or greater than 50, apply an air resistance of 0.03. And those within 5 to 50 will be applied with a gradually changing air resistance. Then we add a pop force. In fact, the air resistance only slows down the velocity. It doesn't cause any disturbance, but forms some weird particle tails. As to the swirl size, we can refer to the previous values we set, or refer to the human model and the buildings. We ever set values like 3 or 5, so you can figure out the proper value based on the effect you prefer. Let's cache it again. Compared with the previous effect, the spray are restricted obviously. I have made a flipbook. Let's watch it. Perfect. We can see a lot of flocculent details in it. If you think they are too dense, you can check Enable Density Control in Whitewater Solver. But if you want a more obvious flocculent effect, you can adjust base advection strength. As to advection by depth, the curve here reflects how much the base advection is applied to the particles in different depths. The middle represents the depth of 0, that is, the place where the foam sits. The left corresponds to the depth below 0, where the underwater bubbles stay. Similarly, the right corresponds to the spray in the air. Mostly, the spray corresponds to the strength of 0, which means it's not affected by the base advection strength. So the flocculent effect is mainly on the surface where the base advection is almost the highest, and none where the spray and the bubbles are. Well, you can edit the curve further if needed. Set base advection strength to 15 for now, and cache it to see what will happen. The flocculent effect is more obvious than before. The current effect is close to the intended effect now. The only concern is the number of particles. They are still insufficient here. One is to reduce the whitewater scale. The other is to increase emission amount. Here I set it as 12. Cache it again. Okay, it's done. We can see obviously more particles than before. There are more than 20 million of particles now, while 4 million in the previous version. Alright, we have basically done with the whitewater in the first box. Its feature is the abundant flocculent details in it, but its flaw is the small volume of spray. We need more spray to increase the volume of the splashes. Yeah, it's hard to get it by adjusting the whitewater, so I'm going to make another pop as mist shrouding the splashes, but it doesn't need too many details. Let's delete these test versions first. Here we use the white water as the pop source. Drop down a dot network. Still set the start frame as -30. Connect white water to the first port of dot. Drop down a pop solver, a pop object, and other necessary nodes. Let's finish the basic settings first. Okay, done with that. Pop source, gravity, ground plane, and 3 static objects. As mist will disappear when falling on the ocean surface, so we don't need the tsunami mesh as the collision object. Let's disconnect static object 3. Then we move on to the pop source. Select points and use first context geometry. Then set constant birth rate. Here we need to take the computer RAM into account. Uncheck max points per frame. Set a small value for life expectancy. Set life variance as 0.7 so that life expectancy ranges between 0.7 to 2.1. Set a smaller inherent velocity to get a tailing effect. Increase variance a bit. We can let it be controlled by the velocity, because if variance is only controlled by a fixed value, the dynamics of the particles won't be random enough. So we let the variance work as per different velocities. We can use an attribute to control variance. Unlock pop source 1 and enter into subsolver 1. Here is the variance node. We replace it. Set the attribute name as scale, the type of which is float. Drop down an attribute ring, go to define scale. Let scale be equal to velocity divided by a value, because the velocity is a very large value. Let's take a look. The maximum is close to 100. So here we divide it by 10. Good now. Next, let's optimize the pop source. Just copy subsolver 1 we made before and modify it slightly. The particles with low velocity are produced by the collision with the tsunami mesh. But the mist doesn't collide with the tsunami mesh, so delete these 2 nodes. Here we can optimize it a bit more. In fact, we only need the mist outside the white water, but the inside part are not needed because it's invisible when rendering. Import the surface field. Here we use volume sample to delete the particles below the surface. Like before, we added pop drag. Here we can control the drag force further through the edge of particles. Otherwise, the drag force is too even. Let's multiply air resistance with h. But the air resistance changes too fast, so we let h be divided by a value. Adjust this curve. So that the air resistance changes gradually. Besides, we set a slightly larger air resistance for mist. Okay, let's go ahead. Drop down a pop force here. Set a larger amplitude and swirl size. Then set a wind force on negative x-axis, the same direction as the tsunami movement. Okay. Before caching, let's delete the unused attributes. Delete detail, primitive, and vertex attributes. We only keep age and velocity here. In fact, you need to evaluate which attributes will be used next. Then we clear all the unused groups. Last step, drop down an attribute cast to compress these attributes. Only compress age and velocity. Here we directly exclude position. We can see some velocities are zero. There should be ground collision object in this step. We simply exclude it through object ID. Here it is. Fixed. Now everything goes well. Let's cache it. Previously, we optimized some particles out beyond camera view. We can see the particles are far away from the camera, so we can delete more. The X offset we set before is a little too large. Set it to 0.1. We delete this line. It was merely for explanation before. This group name should be the same as the name here, so that the particles can be highlighted. Then we cache it once again. Okay, it is done. Display the whitewater. The mist shrouds the whitewater very well. We merge them and take a look. The particles here seems insufficient. Anyway, let's check the overall effect in the final rendering. Let's check the dynamics of the mist. The overall dynamics are almost the same as the whitewater, just its range is larger than the whitewater, but it's good overall, so we keep it for now. Alright, the first whitewater simulation is completed. We just duplicate it for another two parts. Let's duplicate the second part. Then the third one. 3 parts in total. The second and the third parts don't need too much modification. So does the flip here. We can duplicate it from pop source and keep the same settings as the dot above, but the simulation range needs to be modified. Then we need another box for the rest simulation. Duplicate box 1, adjust it slightly. This pop simulation is blocked by buildings in part, so it's fine to let it reach here. Enter camera view to check it. Perfect. Drop down a switch. Let it use box 1 when caching pop 1 and switch to box 5 when caching pop 2. To get them switched automatically, we can input a command in pre-render script to let select input switch to 0 when pop 1 is cached and switch to 1 when pop 2 is cached. Let's rename this switch. Then we set up the file cache pop 1. The pre-render script is to execute the commands before caching. We press Windows and E keys to pop up this command bar. First, we define a variable. Through who.node, find the switch node. Then the parameter input. Finally, specify it to the variable. So now we set pop1 as number 0 and pop2 as number 1. Select Python here, then cache it to see what will happen. We click on Save to Disk in background. OK, done. It can be displayed normally. Nothing wrong with the Python switch we set. Let's go ahead. Show dependency links for selected nodes. Currently, .NET 1 is linked with box 1. For the .NET 4, we need to link it with box 5. It's simple, and we've already made such settings before. Here I will demonstrate quickly. OK. Since this part of pop simulation is in the distant view, we can reduce the simRes somewhat. As to this collision object, no need to keep collision objects in the foreground. There's no interaction between them, so we disconnect it. Regarding the collision with the buildings, there's no need to set it so precise as the previous one. In fact, only this building will collide with the pop. Here it just passes by, and the collision is unnoticeable. The interaction with this building only happens in the negative frames. After the first frame, the interaction is almost invisible, a tiny part in the whole camera view. So we can get rid of the buildings to improve the solving efficiency. Only keep the tsunami mesh here. The general settings don't need much modification. Just increase the air resistance a bit. The value we set in the first part is too small, and the splash dynamics are too fierce. So here we increase the air resistance slightly. OK, nothing else to modify. We solve one frame to check it. Perfect. Let's move on. These nodes are for setting the whitewater source. The rest whitewater is in the distant view, so no need to set too high simRes as the simulation in the foreground. And we needn't simulate it separately. Then we can optimize out some part of the process, reduce the simRes, set voxel size to 0.5. The upstream of this process is not simulated, so we cannot simulate it right now. Let's just load the previous cache for now. The current res is acceptable in the distant view, so keep it for now. Next, we will cache them. Start with this one and then these three. The linking needs to be modified. Let's figure out the specific sim range. We display all the buildings. From the simulation bounding box, we can see at around 90th frame, the collision between tsunami and buildings is over. But we can still see it around this frame. So 90 frames are enough. Let's change it. Modify the linking here as well. Next, let me show you how to cache them in batches. We use fetch node and batch node. This fetch node was produced when we made tsunami before. We don't need it here. We can copy the render node and paste it here. This way, when we click on render here, we are actually clicking on save to disk. Check it here. This way, when there are multiple render nodes, it will cache one first, then the next one when the first one is over. They won't be cached at the same time. We only need to copy the render nodes and paste them here. Repeat this operation for each render node. Then connect them in series. It's a bit time-consuming if there are too many file cache nodes, so I made a tool. We can simply select this cache and click this tool, and it will be automatically added here. One done, 3 to go. The same way, click it. OK. Just connect them. Let's check it. Good. The render order is totally as per the order in this network. We add a geometry node for enabling cache in background. Clicking on render only enables cache in foreground. With this geometry, we can click on save to disk in background. Remember to save your project. All the above fetches also work in the background. Then we can shut down the project. Do not forget to get rid of these paths. Then click on Save to Disk in Background.